This recording is going to be on the transport layer. The transport layer, which is layer 5 of the OSI model, layer 3 of the TCP IP model, just before the application layer in the TCP IP model. So we're going to see how it manages end-to-end communication, establishing connections, and how it decides whether or not TCP or UDP are going to be used, which is not really a decision it makes, but something that it just recognizes based on the application that you are using, and discuss some of the port numbers that are assigned to protocols that we'll be using in the transport layer. Okay, the role of the transport layer is establishing a temporary communication session between two applications and delivering data between them. Basically starting up the conversation and making sure that everything flows well in the conversation. You can see it provides services such as connection-oriented data stream support, reliability, flow control, and multiplexing. And we'll be expanding upon those concepts as we go through the chapter. You can see where this transport layer lies in the TCP IP model. So we've just been through a bit on the internet or network layer for looking at the OSI model. So we're moving our way up to transport, so we're right here between application and internet at this point. The transport layer is responsible for tracking each conversation individually, not getting them mixed up, making sure that all the segments for a conversation get to their destination and get recompiled in the correct order through something called multiplexing that we'll discuss in a little bit. So that's one of the responsibilities we have here for the transport layer. And here we see some of the segments that the transport layer might send. The multicolored segments supposed to be representative of each type of communication we have or conversation we have going on. So it allows you to do multiple things at the same time. Since everything is segmented, you could send a segment or a packet of instant messaging. You can along and mix in a web page packet, IP telephony. You don't have to send all blocks at the same time. That's the purpose of segmentation, is to be able to basically multitask and send different bits of each type of packet at the same time. Okay, going along with that, making sure that if you have multiple applications running on a device, that all applications receive the correct data, because those segments are marked. They have an identifier on them that lets the recipient know which order those segments are supposed to be reassembled in, and which protocol or application should be using that segment that's being sent along the network. So this all goes into a process called multiplexing, basically using those segments to split data up into smaller chunks so that many different types of data can be sent along the network at the same time, as you see with this very detailed multicolored graphic right here. The transport layer does add data to each segment in the header to identify each segment of data, and also to allow different types of protocols to be used on different data segments. We'll see some of those protocols coming up here in a few slides. So you can see the segments down here. So allows us to send multiple types of packets over our network at the same time. Okay, error checking can be performed here. So and that's about it. We'll move right along. So transport layer reliability is going to vary from application to application. We basically have two different transport layer protocols that we use. We have TCP and UDP, and one is more reliable than the other. TCP is the one that's considered reliable, and it when you use that, each device is acknowledging that it's received every single packet that you've passed back and forth, which is nice, but does create more overhead on your network. UDP is just going to try to send things off as well as it can. It doesn't wait for acknowledgement that a packet's got there. It's just going to hope and pray that the packet gets there on time and intact, which is actually more efficient for some communications. And of course, some you do want to be sure that your packets are getting to their destination on fully intact, and that would be more of a TCP operation. You don't want to send an email to somebody that has some words missing, for instance. That's not exactly what would happen maybe, but you want to make sure the email's intact. You want to make sure a web page loads up correctly. If you're transferring a file from one place to another, you don't want a file that's missing some information so you can't open the file at all. Okay, so those are things that you could use TCP for, and you can see some of the applications associated with TCP over here and UDP over there. Okay. So here we have our three basic operations that enable reliability with TCP. Basically, you're going to number and track segments transmitted to a specific, from a host to a specific application. Okay. Once a server receives, let's say, some communication stream from a host, it has to acknowledge the data has been received, and if it doesn't acknowledge some portion of data as being received, the client would retransmit that data if need be. So that's basically what happens. You're going to specifically number those data segments, or you could say packets, that are being sent back and forth, and the recipient is going to have to acknowledge that they've received it, send the acknowledgement back to you so you know you don't have to retransmit, and then you'd retransmit more data if you got confirmation that your recipient had received that first segment of data. UDP doesn't really care about any of that. It's just going to send your data. Reliability is not something that you're going to care about too much with UDP. So you don't get confirmation back that a packet or segment was received in the correct order, that it was received at all. You're just going to keep sending out data and hope for the best results, essentially. This is more practical because it does require less network traffic. You're not sending data basically both ways, waiting for an acknowledgement before you can send your next segment of data. You're just going to keep on sending, keep on sending. For an application like streaming movies, like Netflix or something like that, it's not going to be that big of a deal if you have a small glitch in a couple pixels in your screen. You may not even notice it. I mean, sometimes you get bigger glitches, but for the most part, you're getting all the data you need to. Okay. If you are a gamer and you experience lag, it's because you've probably had some packets dropped through UDP. You see your opponent disappear, then reappear somewhere else, or you thought you shot somebody, and really on their screen, they were a lot further along. It's because there's some packets being dropped somewhere in that process, and you're not quite getting everything. Okay. So it's practical there because you're looking for as much speed as possible. If you're using something like TCP, it would take longer for your packets to be sent. You'd probably experience a lot of people rolling back as you were looking at them on the screen in that case. For instance, think about if you were having a Skype conversation and you have somebody on video repeating things a couple times because the video wasn't sent correctly, so you have to wait for it to be sent in exactly its correct state. So someone could be repeating the same phrase over to you 3 times before they get it right. You really don't care in a Skype conversation. You're just going to ask somebody to repeat themselves if something goes wrong. So rather than waiting for a delay in a video call, you'd use UDP, and well, it always uses UDP because it's not essential that we get every single packet right. As long as we get most of them right, then we're okay. So it's the faster protocol. If you don't need total reliability, you'd go with UDP, and that decision is made by developers' applications, so we don't really need to worry about that as much. So we can see that TCP is a better choice for applications whose segments must arrive in a specific sequence to be processed successfully, in which all data must be fully received before it is considered useful. And some examples: databases, web browsers, email clients. You want to make sure those things are fully intact, that you're not getting a altered version of what you're seeing, what you're reading, altered version of files. UDP is a better choice for applications that can tolerate some data loss, like video streaming, gaming, Skype, video chatting, things of that nature. But delays in transmission are unacceptable. Okay, you might have been on a voice over IP or a Skype conversation where someone you can tell that they've responded, or it's been a long time since they responded, but then you finally hear their response maybe 3 seconds later, and it really messes up the conversation when that happens. So it's still using UDP, it's just the UDP's even not fast enough, maybe if you're too far away. So that would be even worse if you were using TCP. That would be more of a consistent thing, that you would talk and then maybe 4 seconds later your recipient hears what you said, because it's making sure that your entire sentence is intact before it decides to send it all away, essentially. Okay, so not ideal for those type of applications. Again, applications using UDP include live audio, live video, voice over IP, and gaming. Got to throw gaming in there. All right, so we have a TCP and UDP overview here. So some things we saw in the first section here on features of TCP. You got establishing a session ensures the application is ready to receive data. Same order delivery ensures that the segments are reassembled into the proper order. Reliable delivery means lost segments are resent, so data is received completely. Okay. Flow control ensures that the receiver is able to process the data received. Okay, and you work with a certain window of data in order to make sure that's happening correctly, which will be coming up pretty soon here. Okay, here is our TCP header. If you remember when we discussed the way data flows through your network, you go from top, you get your application header, you have a transport layer header that gets put on that, we have a IP header, a frame header at the data link layer as data flows down through the protocol stack. And we've talked about IPv4 headers versus IPv6 in previous chapters. Here is our TCP header. So we have a source port, which most of the time ends up being a randomly generated port in this dynamic range of ports that are available to you. You have a destination port, which is going to be most often predefined, like you would have HTTP would be a port 80, FTP would be a port 21, I believe it is, so on and so forth. You have a sequence number for each segment of data. So which sequence number do we have on this? What sequence does the recipient reassemble these segments in? Okay, we've got a window, which is basically what is the window size for your how much data you can send before you get an acknowledgement back, essentially. Okay, and you'll see that a little bit better in a future slide. Checksum for error checking, so on and so forth. All right. So we got our UDP features, no order data reconstruction. Data is reconstructed in the order that is received. Okay, so That can lead to problems because sometimes all of your data segments don't take the same path from one place to another. You might have a best path available, but then one of the routers in the best path available gets congested, and you take another route around it because that path becomes better, and then things can get out of sequence, and that way data can become slightly corrupted. It typically doesn't do anything too major, but that doesn't happen too often, but it can. No session establishments, connection lists. It doesn't check, oh, are you there? Can you receive data? I don't care. I'm just going to send data and hope it gets there. If it doesn't, it'll go through its time to live and die eventually. So UDP does not care. Unreliable delivery, any segments lost are not resent. Okay, you just keep on sending out those segments. It doesn't matter. You don't wait for a reply. You just keep on sending data. No flow control does not inform the sender about resource availability. Okay, so if the timings have changed or a network is slowed down, we don't know. We just keep sending at the same rate, no matter what. So there's no checking of any sort going on with UDP. So we can see the UDP header is a lot smaller than the TCP header was. Our TCP header was 20 bytes. UDP header is 8 bytes. There's no error checking, no window size. A lot of things are missing in UDP that were in TCP, which makes it lighter though, easier to handle. So since you have to send data quickly, this is a ideal situation. Okay, pieces of communication in UDP are called datagrams, and these datagrams are sent as best effort by the transport layer protocol. The applications must ensure that the data has arrived correctly or be able to tolerate some data loss if there is some, because with UDP, some points there will be some data loss. So that's on the end of the application to make up for. For instance, when playing Street Fighter, if there are some dropped frames or dropped segments, sometimes it'll roll back your fight for like a quarter of a second. So what you thought you might have sweeped somebody, it actually ends up that they jumped over you and kicked you in a cross-up. So there are usually tolerances in place by applications in order to compensate for data loss. You might notice that if your network slows down watching Netflix, things get pixelated for a second, but then it catches up and it turns back to 1080p, full and clear. So there are things in place to try to tolerate some data loss with UDP. So we have these segments, multiple instances of them being sent over our network pretty much constantly. And we need a way to manage these multiple conversations. And there's an identifier for that in your TCP or UDP header that allows you to handle multiple segments being sent. And those, the identifiers are port numbers. Which port is that information, that packet, that segment going into? Okay. For instance, we have electronic mail, which is port 110, HTML, port 80, internet chat, port 531. I think that's an AOL Instant Messenger window. Nobody uses that anymore. Anyway, you do have different ports that your information will be heading into, and that's how you can manage multiple separate conversations through different port numbers, or at least that's one of the ways that you're able to manage those multiple separate conversations. So we have a source port and a destination port. You have a source port which is not predefined. It's technically random, dynamically chosen, but really, I guess nothing on a computer is ever random. There's some calculation being made to make that number. But it is pretty much a random number. And that's your source port for a particular segment or packet. Okay. It's in the segment header that you'd see that, the TCP or UDP header. The destination port is going to be assigned for the specific application that you want, whether it's HTTP, FTP, POP3, STMP. whatever protocol you're requesting information from or trying to establish communication with. Now, you might be processing multiple HTTP conversations at the same time. Maybe you've got two web pages running at once. So when you send to an HTTP port on some server, it knows, in order to keep those conversations managed, to send that information back to the port, the source port that was attached to that data. That way, on your end, you're keeping your conversations separate from each other, because you're not going to assign the same source port to your two different HTTP packets that have gone out there. Okay, so that's one way that we're keeping conversations separate from each other, through ports. Also, if a server performs multiple services, if it does a FTP and it also has a web service on port 80, that destination port number is going to tell the server what type of information you are requesting from it, and keep its own traffic separate through using those port numbers. So port numbers are actually pretty important here. Also, I mean, on the CCNA exam, we don't go over it too much here, but you are going to want to know the common port numbers for HTTP, POP3, FTP, things of that nature. We saw a list of those back in, I think, chapter 2 or 3. I can't remember which one off the top of my head. The combination of your source IP and source port number is known as a socket. So basically, a port and an IP address together are what is known as a socket. So basically what you do is take your IP address, then add a colon at the end, and add the port number that is associated with that IP address. So we can see in the example here, this port IP address and port number there lines up with the segment that we have here, actually the frame that we have down here. Okay, so we take this source IP, source port, that's how we get this number, destination IP, destination port, that's how we get that number, and that number is considered a socket. Okay, and you put the destination and source together, we get a socket pair. Okay, you may have heard the term on a TV show or something like that. Can you open up a socket for me on your server? It's just saying, can you open up maybe if they want a file transfer protocol, open up a port number 21 for my IP address to connect to your server. So when you have opened a socket, basically you've opened lines of communication from one place to another. Okay. Transport layer keeps track of which sockets are open and are communicating. So again, if you have a server that performs multiple services, you can have different sockets open on each service, or multiple sockets open on each port for each service. So important thing, basically remember that your IP address along with a port number is considered a socket, and it's a way to manage multiple connections. So we have different port number groups, and it's going to be important to remember the range of these groups. Assigned by the Internet Assigned Numbers Authority, IANA, responsible for assigning various addressing centers, including port numbers. So basically we have is well-known ports, 0 through 1023. Most of them have some type of application assigned to them, so they're well-known ports. Registered ports would be ports that kind of your computer can randomly generate to receive data on as they establish a connection to one of those well-known port numbers. Okay, you may have noticed that basically these ports that were assigned here, 1099, we've got 1305, that falls in this registered ports range. You've also got private and or dynamic ports, and those might be ports that you use when you're trying to open a port for some application on your computer. You can still use the registered ports. Basically, what you can't use is this well-known ports range. Okay, so these aren't really too different from each other. You can use them for different applications. But most often when your computer assigns a random port to a session, then it's going to use one of this registered ports range. Your netstat command is basically going to show you your active TCP sessions. A unexplained TCP connection can indicate a major security threat. Somebody's getting into establish a session with your computer that you didn't know of. They could be stealing data. They could be installing malware. Who knows? So that can be an indication of a major security threat. You can see here you don't get complete addresses. Down here we've got a local address, which is basically a combination of your host name and your real address. If you want to see complete addressing information, instead of netstat, you can do a netstat-n. That would show you complete addressing information in your netstat command. All right, so we got through there basics of TCP UDP. Now let's get into some more specifics of TCP and UDP. Okay, so we start with TCP. So the TCP server process, each application process running on the server uses a port number. An individual server cannot have two services assigned to the same port number within the same transport layer service. Meaning that if you're using TCP or UDP, you can have the same port number assigned to a service that's using TCP, then a same port number assigned to the service using UDP. You just can't have two TCPs on the same port or two UDPs on the same port is what it's saying there. An active server application assigned to a specific port is considered to be open. Okay, that would be opening a port for some application. Okay, if it's assigned to a specific port. Any incoming client request addressed to an open port is accepted and processed by the server application bound to that port. Okay, so if you send something to HTTP, it's on port 80, it's going to be processed by that HTTP application. Okay, there can be many ports open simultaneously on a server, one for each server, active server application. So this is the process of establishing a TCP connection. Nothing's actually being sent yet. We're just establishing that the connection is there before we start to send any packets back and forth. So basically what's going to happen is client A is going to send a sync message to server B. So basically asking, are you there? Are you ready? Are you there and able to communicate? And so client P receives that, says, yes, I am here, able to communicate. Do you want to, I'm going to send a message back to you asking you if you're ready to establish this communication with me as well. And it is sent back to the client, who acknowledges the server to client communication and sends that back to the server. So basically A sends to B, B sends to A. They both acknowledge the communication session. Once that's all taken place, then we're ready to start sending things back and forth. So we're setting up a communication session between your client and your server by saying, basically, from 1, are you there? Server B, yes, I'm here. I'm going to send a server to client communication session acknowledgement back to you. Okay, got it. I know that you're there. Now I'm going to acknowledge that you are there from your request and start sending packets to you back and forth. So again, here, are you there? Yes, I am. Establishing communication with you as well. All right, got it, acknowledged. Now I'm going to start sending packets your way. Okay, let me back up real quick. So when you're establishing a connection, you're sending a SYN, or sync, you can think of it as, and then in sync acknowledgement, you got a SYN ACK. Okay, that's an acknowledgement. All right, that acknowledgement is received by your client again, and that means that we're ready to establish communication and start sending data back and forth between each other. Okay, so SYN ACK, and another acknowledgement down here. Okay, when you're done sending communication back and forth, then we get to fin and finac. So that's finishing the communication. So that's how you can see it. So I've got sending this finished. Okay, I've sent all the information back to you that I need to. So you send this fin over here. Okay, I acknowledge that you've sent this fin. So I get this fin acknowledgement that is sent back. I acknowledge. I send the fin here. Okay. I see that you've ended the session on your end, so I'm going to acknowledge that you've ended as well, and that finally terminates the communication. Okay, so basically, up here again, I've finished. I'm going to tell you I'm finished by sending this fin. Okay, I see that you're finished. I acknowledge that you're finished, and I send that finish acknowledgement, finac, back to you. This fin's received here. I know it seems redundant, but then I'm going to say, okay, I've acknowledged that you've that you recognize that I've finished the session, and that's the final step. Okay, I acknowledge this last fin that you sent, and session is closed. Seems a little bit more than it needs to be, but it all happens in basically a nanosecond, so it's just the way that TCP works. So this three-way handshake that is taking place is all, if you're looking at your TCP header in this control bits section down here. Now remember, this is going to be TCP because UDP, you don't do this handshake. You just start sending data. So it establishes that the destination device is present, verifies that the destination device has an active service, and is accepting requests on the destination port number that the initiating client intends to use. Okay, in this case being destination port 16. Informs the destination device that the source client intends to establish a communication session on that port number. Okay, so you've got that going on. You can see those things we were just talking about: ACK, acknowledgement, SYN, synchronized sequence numbers, fin, no more data from the center. So some of those things are over here. You probably want to know what those mean. Reset the connection, push function. URG for urgent pointer field significant. Okay. Really the only ones we'll deal with here are fin, ACK, SYN. Okay. So reliability and flow control. So we have this ordered delivery, which basically is going to take your segments, attach numbers to them, and then reassemble them, making sure that everything arrives in the correct order. So essentially, before you see anything on your screen, all of these segments have to arrive in their totality. So once your data unit, or your data in general is reassembled, then it comes onto your screen, which is why you don't want this for video streaming, gaming, and things of that nature, because you'd have jumps possibly in the video as you're waiting for all of your segments to arrive. If you're gaming, you're going to have jumps in the game because you're waiting for all data to arrive, not just streaming it constantly. Okay, so basically what happens is the recipient receives data segments 1, 2, 3, 4, 5, 6. Once it receives everything in that block of data, then it finally shows something on your screen. It doesn't just show partial data as it's coming in. So you have to wait till all data is assembled, then these segments all get pushed up to the application layer, and you get to see something on your screen, or you receive the data through FTP or whatever it is that you're looking to do. Okay, so nothing's out of order. Everything's marked as it should be. How things can get out of order is you can see different segments may take different routes to get to your recipient over here. So if that does happen, your segments could become out of order. Also, these segment numbers are incremented based on the number of bytes transmitted. So it's randomly chosen during the TCP session setup, and these numbers are incremented by number of bytes transmitted. So that's how ordered delivery pretty much works. Each segment gets a number. They're reassembled at the recipient in the transport layer. Once they're fully reassembled, then that data gets pushed up to the application layer where the recipient can see it on screen or interact with it. It's actually shown on the computer, whether it's a file transfer, web page, email, whatever. Okay. All right, TCP reliability, sequence, numbers, and acknowledgements. So TCP is designed to confirm that each segment has reached its destination. Yes. TCP session setup ensures that the destination is not only reachable but ready to receive data, because you get some acknowledgement back from the recipient or server saying that, yes, I've acknowledged and I'm ready to receive. The TCP process on the destination host acknowledges that data it has received, the data that it has received from the application. So as you're sending packets and segments of data over to the destination host, it does say, yes, I've received this, I've received that, letting you know whether you need to retransmit or not. TCP does allow for the retransmission of missed segments. So yes, you will end up retransmitting if some data is lost in the process. TCP ensures all segments are properly reordered upon receipt. We just saw that in the last couple slides. TCP session termination allows for parties to gracefully end a TCP session when no data is being transferred, with that fin that we saw to end the session. Okay. Sometimes when you have router issues, it can be because you have open sessions and not even know about it at your home, on your home routers. And basically, when you would unplug your router, that would flush all of your open sessions essentially. So that can be one of the issues that comes up on your home routers. A TCP endpoint can abruptly terminate a session if necessary. Okay, so that is something that you can do. Maybe you notice a TCP session that's open on your device. If you do a netstat and you want to terminate it quickly, you've got this RST flag that we'll discuss a little later on, allows you to do so. Okay, and if you want to see the video, that it is in the online materials. So TCP does provide methods for managing segment losses, data loss. Among these methods is a mechanism to retransmit segments for unacknowledged data. Okay, I'll try to explain that a little bit on the next slide that shows you a bit more on this topic. All right, window size and acknowledgement. So TCP provides mechanisms for flow control. One of them is window size. A window size determines how much data you can send to a recipient before receiving an acknowledgement of the data. Okay, so this window size is a number that is generated between the two hosts or the host and the server, whatever you have on each end of the communication. All right. So here, what do we have? A window size of 10,000, it looks like. So you could send 10,000 bytes of data back and forth before you receive an acknowledgement. So I send 1,400 bytes, then 1,400 bytes, and the recipient acknowledges, okay, I got all 1,400, or sorry, yeah, all 1,400 bytes of that data, or that's 1,400 together would be 2,921 bytes. Okay. So we have congestion avoidance here. This is something that's handled on the source side based on acknowledgements that the source is getting back from its destination. So if I'm sending segments to my destination and I send four segments, but I'm only getting back an acknowledgement that the recipient has received 2. I know that there must be some network congestion going on, not allowing it to receive that full window worth of acknowledgements. So I'm not going to adjust the window size. That would be on the part of the destination. What I'm going to do is see that, okay, I'm not able to get that many segments through before receiving an acknowledgement. So I adjust how many bytes I'm sending over the network before I send more. So on my source side, as I'm sending things to my recipient, PCA to PCB over here, I'm going to decide I'm just going to send 2 segments at a time now, because as I'm sending 4, I'm getting an acknowledgement back that it can only process 2. It's only acknowledging 2. And I'm having to retransmit all the time, which is going to make network congestion worse. If I'm sending 4 segments and it's only acknowledging 2, there's pretty much 2 segments worth of bandwidth I'm eating up, and I don't need to because they're not being recognized anyhow. So I'm just going to adjust and send 2 segments at a time, and then hopefully get those 2 segments acknowledged and just go through the process like that. So the destination doesn't see that congestion going on, so it sees no need to suggest a new window size. Therefore, it's the responsibility of our source rather than the destination to adjust the amount of bytes it's sending over the network. And we have UDP. So UDP does have its benefits. It's just not reliable on a transport layer level, though. It can be reliable at an application layer. So UDP is a simple protocol. It provides the basic transport layer functions, much less overhead than TCP because there's no acknowledgement, there's no establishing a session, there's no finishing a session. You're just sending data. UDP is not connection oriented. It does not offer the sophisticated retransmission sequencing and flow control mechanisms that TCP does. Applications running UDP can still use reliability implemented by the application in the application layer. It's not inferior. It's designed to be simpler and faster than TCP at the expense of reliability. Okay, so UDP, you need to send things. It's fast. It's not so crucial that every single segment gets there intact. Every packet doesn't get there intact. Then we use UDP. So at the transport layer, there's no ordering, no sequence to your datagram, which is what you get in UDP. Rather than segments, you got datagrams. No reassembling into the correct order. It's just received in the order that it is. If something's dropped in the process, nothing's resent. So the application is going to have to do its best with the information that it has available, essentially, with UDP. So you can see what we've got down here as far as our datagrams being sent and not particularly being in quite the correct order there. So the way port numbers are handled with UDP are basically the same. There are specific port numbers applied to the UDP applications. So it's really no different than TCP as far as port numbers go. It's going to be sent to a certain port number on a server. Based on the port number, it's going to be associated with a certain application. Okay, so nothing too different from TCP there. Okay. So again, nothing all that different. UDP client server communication is also initiated by the client application. UDP client process dynamically selects a port number and uses that as its source port, just like TCP. The destination port is usually the well-known or registered port number of the app assigned to the server process. So whatever. I'm not sure what the port number is for video chat and things of that nature, but it would be a predefined port number. The same destination pair of ports is used in the header of all datagrams used in the transaction, and they basically just flip as data returns to your client from the server. So your source becomes your destination port, your destination becomes your source port in the UDP server process. So again, not so complicated there. So the big question, TCP or UDP? So TCP handles all transport layer related tasks. This frees the application from having to manage any of these tasks on its own. Applications can send the data stream to the transport layer and use the services of TCP to make sure everything's arriving intact, in the correct order, that data is retransmitted, and it's presented as it was meant to be without the application having to do any of that work. So TCP, again, some processes associated with TCP, HTTP, FTP, SMTP, Telnet, all require that data is 100% in the form it was sent in. Okay, applications that use UDP. Some of them, we've discussed them before. Live video multimedia applications, voice over IP, simple requests and replies, applications with simple transactions where the host sends a request and may or may not receive a reply. These include DNS or DHCP. They use UDP. Applications that handle reliability themselves, unidirectional communications where flow control, error detection, acknowledgements, and error recovery is not required or can be handled by the application. This includes SNMP, TFTP, Trivial File Transfer Protocol, and over here we have some examples of applications that would use UDP. So we got IPTV, Voice over IP, TFTP, NMP, DNS, and DHCP are all some protocols that use UDP. Okay, you just want to remember for the test which ones would be associated with TCP, which ones would be associated with UDP. Reliable, faster. That's what we got. And that's about it. So we went through TCP and how it's reliable, how it can retransmit and whatnot. Also we had UDP, which is less reliable, but can transmit a lot faster than, and requires less overhead than TCP. Okay, so that's it for Chapter 9.